Our universe was forged in chaos. Cosmic catastrophes are the violent architects of everything we know. This journey through 20 universe-altering events will show you exactly how our cosmos evolved from a single point to its current vast expanse. You will discover the hidden forces that dictate the fate of galaxies and life itself. We will uncover why a tiny imbalance between matter and antimatter allowed anything to exist at all, and how the death cries of the first stars seeded the cosmos with the very elements that make up our bodies. This story connects the largest explosions in history to the air you are breathing right now. How do you think a single cataclysm billions of years ago could have led to you being here today? Before anything else existed, there was a point of infinite potential. This was the singularity, a state of such extreme density and temperature that the very laws of physics as we know them break down. It was not an explosion happening within a void, but the sudden, violent emergence of space and time themselves. From this incomprehensible beginning, the universe began to expand and cool at a staggering rate. In the first fleeting moments, the fundamental forces that govern reality, like gravity and electromagnetism, were forged from a single, unified power. This initial state was a searing hot soup of energy and the most basic particles, a chaotic primeval fire that contained the blueprint for every galaxy, star, and planet that would ever form. One of the most profound pieces of evidence for this event is the cosmic microwave background radiation. Think of it as the fading afterglow of that colossal birth, a faint whisper of heat that permeates all of space. This relic radiation was predicted by theory and then accidentally discovered, providing a tangible snapshot of the universe when it was just a newborn. The patterns imprinted within this ancient light reveal the subtle seeds of density, the tiny fluctuations that would, over billions of years, collapse under their own gravity to form the vast cosmic web of galaxies we see today. So the distribution of matter across the heavens, the very fact that we have stars and worlds instead of a perfectly uniform haze, was dictated by the initial conditions of the Big Bang. Every structure we observe is a direct consequence of that first catastrophic genesis. How incredible is it that the fate of trillions of suns was decided in the first fraction of a second of existence? This foundational event set the entire cosmic drama in motion, but the universe was still a formless, elementary place. It would take another universe-altering catastrophe to begin building the world we recognize. Yet this newborn universe faced profound riddles. Why does the distant cosmos look so similar in all directions, as if every region had once been in contact? And why does the overall geometry of space appear so perfectly balanced, neither curling in on itself nor flying radically apart? The answers lie in a second, even more violent catastrophe. For a fleeting instant, the universe underwent a growth spurt of unimaginable ferocity, expanding faster than light itself. In less than a trillionth of a second, a subatomic speck of space was stretched to a size larger than our entire observable universe today. This explosive event, known as cosmic inflation, was the universe's ultimate makeover. It ironed out the primordial wrinkles, creating the stunningly smooth and uniform cosmos we observe on the largest scales. But it did not create perfection. Inflation also magnified tiny quantum jitters, the ghostly flickers of energy that exist even in a vacuum. These microscopic fluctuations were stretched to astronomical proportions, becoming the subtle seeds of gravity. They were the faint blueprints for everything to come. Every galaxy, every star cluster, every vast cosmic web of dark matter owes its existence to those quantum seeds planted during inflation. Without that frantic burst of expansion, the universe might have remained a formless, featureless sea of particles, or it might have collapsed back in on itself almost immediately. Instead, inflation set the stage, creating a universe that was both smooth enough and lumpy enough for greatness to eventually emerge. It solved the horizon problem by ensuring distant regions shared a common origin before being flung apart. It solved the flatness problem by stretching the fabric of spacetime so thin that any initial curvature became negligible. In essence, inflation wrote the rulebook for how the cosmos would grow up, a foundational template that every subsequent catastrophe would follow. But this beautifully structured universe was almost entirely erased before it could truly begin. In the first searing moments after the Big Bang and inflation, the cosmos was a perfectly balanced and therefore doomed place. For every particle of matter that popped into existence, a mirror image particle of antimatter was created alongside it. Think of them as cosmic opposites, identical in every way except for their charge. When a particle of matter meets its antimatter twin, they do not simply bump into each other. They vanish in a spectacular flash of pure energy, a total conversion of substance into light. This process, annihilation, is the most efficient and destructive reaction in the universe. In that early, dense furnace, matter and antimatter were constantly meeting, constantly destroying one another. If the universe had remained perfectly symmetrical, this mutual destruction would have been total. Every last proton, every electron, every quark would have found its antimatter partner and been erased. The cosmos would be left as a lifeless, expanding fog of radiation, with no material left behind to ever form a single atom, let alone a galaxy or a living being. Yet here we are. So what happened? Somehow, in that furious chaos, a cosmic crime occurred. For every 1 billion pairs of matter and antimatter that annihilated each other, a single, solitary particle of matter was left behind. A 1 in a billion surplus is all that survived the Great Annihilation. That infinitesimal imbalance, that tiny broken symmetry, is the only reason anything made of atoms exists today. Every star you see, every planet you stand on, every molecule in your body is made from the leftover debris of that near-total destruction. We are the survivors of a war that wiped out almost all of existence. The precise mechanism that tipped the scales remains one of the most profound puzzles in all of physics. What fundamental law of nature was slightly biased, favoring matter over antimatter just enough to allow for a material universe? Scientists search for the answer in the behavior of exotic particles and the conditions of the early universe, hoping to find a crack in the perfect mirror of physics. This first fragile victory for matter set a crucial precedent. It proved that the universe could evolve from simplicity to complexity, but only through catastrophic imbalance. The stage was now set, populated with a sparse but vital supply of raw material. The next great challenge would be to turn that raw material into something more. For nearly 400,000 years, the universe remained a searing, opaque fog. Light was a prisoner, trapped in a relentless dance with a sea of free electrons and protons. A photon could not travel even a minuscule distance without being scattered, absorbed, and re-emitted by this charged plasma, turning the entire cosmos into a brilliant, impenetrable glow. But then a profound cooling occurred. The universe expanded and cooled to a temperature of around 3,000 degrees, a threshold that allowed for one of the most transformative events in cosmic history, a process called recombination. This is the moment when free electrons finally slowed down enough to be captured by protons, forming the very first stable, neutral atoms, primarily hydrogen. It was not a sudden explosion, but a quiet cosmic settling, a great neutralization of the charged particle soup, With this single change, the universe became transparent. The fog lifted. The photons that had been trapped for millennia were suddenly set free, streaming across the cosmos in every direction without obstruction. This great liberation of light is what we observe today as the cosmic microwave background, the afterglow of that moment of clarity. That ancient light is a perfect snapshot of the infant universe, and its subtle variations are a frozen record of the density seeds planted by inflation. But this new transparency came with a profound consequence, the beginning of the cosmic dark ages. With all the primordial light now streaming away and no stars yet born, the universe plunged into an era of literal and figurative darkness. The neutral hydrogen gas that now filled space was largely invisible, and for millions of years the cosmos was a vast, dark, and simple place. It was a quiet stage, swept clean and set for the next dramatic act, the birth of the very first stars. Out of the cosmic dark ages came the first true lights, and with them the first true deaths. These primordial stars were not like the sun. They were colossal behemoths, hundreds of times more massive, burning their nuclear fuel with a ferocious and fleeting intensity. Their lives were short, and their ends were the defining catastrophes of a young universe, when the core of such a star could no longer withstand its own immense gravity. It did not simply fade. It collapsed in upon itself in a fraction of a second, then rebounded in a blast of unimaginable power, a supernova. This was far more than a stellar explosion. It was the universe's first great act of creation. Within the heart of that detonation, under temperatures and pressures greater than anything since the Big Bang, the very elements of life were forged. The simple hydrogen and helium from the beginning of time were fused into carbon and oxygen, into silicon and iron. Every atom of oxygen you breathe, every speck of carbon in your body, every piece of iron in the ground beneath your feet was created in the nuclear furnace of a star that lived and died long before our sun was even a glimmer in a nebula. These first supernovae were cosmic forges, scattering their newly created riches across the void. They polluted the pristine hydrogen clouds with the raw materials for rocks, for oceans, for air. They transformed the universe from a simple place of two elements into a chemically rich environment, capable of building complex worlds. But their role did not end with mere enrichment. The titanic shockwaves from these explosions raced through space for millions of years, acting as cosmic snowplows. They slammed into vast, quiet clouds of gas, compressing them and triggering their gravitational collapse. Each stellar death became a catalyst for new stellar births, a self-perpetuating cycle of creation and destruction. The seeds of future galaxies, including our own Milky Way, were not just planted by the quantum ripples of inflation. They were hammered into shape by the shock fronts of these first supernovae. The legacy of those first stellar deaths is written in the very chemistry of our existence. We are not just stardust, we are the inheritance of the universe's first and most violent sacrifices. What began as a catastrophe of unimaginable scale ended up laying the essential groundwork for everything that was to come, including the potential for life itself to one day ask how it all began. That great darkness did not last forever. A new dawn was coming, one that would fundamentally reshape the cosmos a second time. This was the era of Re-ionization, a universal illumination driven by the most powerful objects in the young universe. As the first galaxies ignited, their brilliant, massive stars flooded space with a torrent of ultraviolet radiation. Elsewhere, the voracious supermassive black holes at the hearts of quasars poured out even more intense energy. This radiation was so fierce that it did not simply light up the darkness. It physically tore the universe apart, atom by atom. It slammed into the vast sea of neutral hydrogen that had filled space since recombination, and it violently stripped electrons away from their protons. The calm, neutral gas that had made the universe transparent to the cosmic microwave background was now being blasted back into a searing, ionized plasma. This was not a return to the initial hot, dense soup of the Big Bang, but the creation of a new, ultra-diffuse plasma that now permeated the immense voids between galaxies. Re-ionization marked the end of the cosmic dark ages and the true beginning of the universe as we recognize it today. It is the reason why the space between galaxies is now largely transparent to most forms of light, allowing our telescopes to peer across billions of light years. But this great illumination was more than just a cleaning of the windows, it was an engine of change. By heating the surrounding gas, re-ionization put a stop to the formation of the smallest, faintest dwarf galaxies. The extra heat made it harder for gas to cool and collapse in small pockets, effectively setting a minimum size for future galaxy formation. This cosmic pruning by ultraviolet light helped sculpt the population of galaxies we see in the local universe. The process was not instant or uniform, it was a patchy, evolving frontier of light eating its way through the shadows over hundreds of millions of years. Understanding this universal transition is like finding a crucial chapter in the cosmic history book, one that explains how the dark, simple universe of the first stars transformed into the clear, structured cosmos we observe today. This second dawning, born from the catastrophic radiation of the first luminous objects, paved the way for the full complexity of the cosmic web to emerge, setting the stage for even larger structures to take shape. The serene spiral of a galaxy is an illusion of cosmic timescales. In reality, the universe is a grand ballet of colliding giants, a dance where the most beautiful structures are born from violence. Throughout cosmic history, galaxies have frequently slammed into one another, drawn together by their immense mutual gravity. These are not quick, fiery explosions, but slow, majestic car crashes unfolding over hundreds of millions of years. During a merger, the delicate spiral arms of a galaxy like our own Milky Way are the first to be torn apart, stretched into great streaming tails of stars and gas by immense tidal forces. This cosmic chaos is not purely destructive, it is a creative furnace. The violent compression of vast clouds of gas within the colliding galaxies triggers ferocious waves of new star formation, lighting up the galactic wreckage with the brilliant blue light of newborn stellar clusters. These stellar nurseries are far more intense than anything in a quiet, isolated galaxy. Yet this burst of life comes at a cost. The same gravitational turmoil can also strip a galaxy of its very lifeblood, its gas, flinging it out into intergalactic space and quenching its ability to form new stars for eons. Alternatively, the collision can funnel enormous amounts of gas directly into the galactic core, feeding the supermassive black hole that resides there. This influx of fuel can awaken a dormant monster, turning it into an active quasar that outshines the entire galaxy, a beacon of destruction that regulates galactic growth from within. Our own Milky Way is a living testament to this violent history. Its halo is littered with the shredded remains of smaller galaxies it has consumed, and it is irrevocably falling toward a future merger with the Andromeda Galaxy, a collision that will reshape both into an entirely new, likely elliptical, galaxy. This transformation is a key outcome of these mergers. The graceful, spinning disk of a spiral galaxy is fundamentally disrupted. The ordered orbits of its stars are randomized, the angular momentum is redistributed, and what emerges is a featureless, football-shaped elliptical galaxy, a quiet retirement home for aging stars. These cosmic collisions are not mere accidents, they are a fundamental driver of galactic evolution. They build up the largest galaxies in the universe, dictate the lives and deaths of stars, and govern the growth of the supermassive black holes at their hearts. They are the ultimate demonstration that chaos and destruction are not opposites of creation, but its essential partners. If the gentle dance of stars within a galaxy is a waltz, then a galactic merger is the most violent, creative, and transformative tango the universe has ever known. Deep within the hearts of most galaxies, including our own, sleeps a monster, a supermassive black hole, a gravitational sink so profound that not even light can escape its grasp. For most of a galaxy's life, this beast slumbers in relative quiet. But when a fresh torrent of gas and stars is funneled its way, perhaps by a galactic collision, the monster awakens. It begins to feed, and in its feeding, it becomes one of the most terrifyingly luminous objects in the cosmos, a quasar. This is not a simple feast, it is a catastrophic eruption. As matter spirals at near light speed into the black hole's accretion disk, it is compressed and heated to millions of degrees, unleashing a blast of radiation that can outshine every star in its host galaxy combined. For a brief, brilliant phase, this single point of light can be seen across the universe, a beacon of raw power. Yet this incredible luminosity is only a side effect of the true catastrophe. The real drama unfolds in the colossal winds and jets that the quasar blasts outward. These are not gentle breezes, but streams of charged particles and radiation moving at relativistic speeds, carrying enough energy to scour a galaxy clean. They slam into the vast reservoirs of cold gas, the very raw material for new stars, and heat it to such extreme temperatures that it can no longer collapse under its own gravity. This process, known as quasar feedback, is the monster's way of regulating its own growth. By violently heating and expelling the galactic gas, the quasar effectively starves itself, cutting off its own future food supply and quenching the formation of new stars across the entire galaxy. It forces the galaxy into an early retirement, transforming it from a vibrant, star-forming spiral into a quiet, red and dead elliptical. The influence of a single quasar does not stop at the borders of its own galaxy. Its energy can pour out into intergalactic space, heating the thin plasma that fills galaxy clusters and preventing that gas from cooling and falling onto other member galaxies. In this way, a single awakened monster can dictate the evolutionary fate of thousands of galaxies around it, imposing a ceiling on growth for an entire cosmic neighborhood. This violent quasar phase is a crucial, if destructive, part of a galaxy's life cycle, a fiery adolescence that ultimately shapes its mature, settled form. It forges an intimate link between the smallest point of infinite density and the largest structures in the universe, proving that the heart of a galaxy can hold the power to reshape the cosmos itself. Even the most violent quasar is a slow-burning candle next to the universe's true fireworks. Gamma-ray bursts are the most powerful explosions since the Big Bang itself. For a few fleeting seconds, these events can outshine every star in 100 billion galaxies combined, releasing more energy than our Sun will over its entire 10 billion-year lifetime. They are the final, desperate screams of dying stars, or the catastrophic collisions of the universe's most dense objects. One type occurs when a truly massive, rapidly spinning star collapses at the end of its life. Its core does not just form a black hole, it funnels its entire dying energy into a pair of narrow, opposing jets that tear through the star at nearly the speed of light. When these jets break through the stellar surface, they unleash a focused beam of the highest energy radiation in existence, gamma rays. Another type is born from the merger of two neutron stars, the crushed cores left over from supernova. As these ultra-dense spheres spiral into each other, they rip themselves apart, flinging out material and again powering a pair of deadly jets. For the brief duration of the blast, a gamma-ray burst becomes the brightest object in the observable universe, a lighthouse beam sweeping through the cosmic dark. If such a beam were to be pointed directly at Earth from within our own galaxy, the consequences would be apocalyptic. The intense radiation would not scorch the planet's surface, it would chemically shred our protective ozone layer. The sky would become a lethal window, allowing the sun's full ultraviolet radiation to pour in, devastating the food chain by killing phytoplankton in the oceans and triggering a global mass extinction. We see evidence in the fossil record that suggests such an event may have occurred hundreds of millions of years ago. Yet from a safe distance, these catastrophes are invaluable tools. Their extraordinary brightness makes them visible from the very edge of the observable universe, allowing us to probe the conditions of the first stars and galaxies. The fading afterglow that follows the initial flash acts as a cosmic forensic tool, revealing the composition of the material the jet is plowing through. It is in the chaotic aftermath of a neutron-star merger that we believe the universe forges the heaviest elements, like gold, platinum, and uranium. The gold in your jewelry was likely born in one of these brief, unimaginably violent cosmic collisions. These fleeting flashes are more than just stellar death throes. They are the universe's most extreme laboratories, momentarily illuminating the laws of physics under conditions we could never hope to recreate. The most violent dance in the cosmos ends with a silent, universe-shaking tremor. When two galaxies merge, their central supermassive black holes, each weighing millions or even billions of times more than our Sun, are drawn into a final, fatal waltz. They begin to orbit one another, slowly at first, but with each pass they steal a little energy from their own motion. This energy is not carried away by light or sound, but by something far more fundamental, ripples in the very fabric of space-time itself. We call these ripples gravitational waves. As these colossal black holes spiral closer and closer, they whip space-time around them like a spoon stirring a vast, invisible honey, sending out waves that travel across the universe at the speed of light. This process drains their orbital energy, sealing their fate. In the final moments before they become one, they plunge together at a significant fraction of light speed. The merger itself is a storm of unimaginable violence, a brief flash where the single, new black hole can release more energy in gravitational waves than all the starlight in the observable universe combined. This is not a flash of light you could see with your eyes, but a shudder that passes right through you, through Earth, through everything. The aftermath of this cosmic union can be just as dramatic. The newborn black hole can receive a powerful kick from the uneven blast of gravitational waves, like the recoil from a cannon. If the kick is strong enough, it can be ejected from the galactic center entirely, sent wandering through its own galaxy as a dark, homeless titan. This event fundamentally reshapes the galactic core, altering the orbits of millions of stars and changing the gravitational heart of the entire system. While we have not yet detected the low-frequency rumble of supermassive black hole mergers, a new generation of observatories is being built to listen for them. These space-based detectors will open a new window into the most powerful events in the cosmos, allowing us to hear the echoes of these ancient collisions and trace the growth of galaxies across cosmic time. The universe is still ringing with the memory of these titanic impacts, a vibration woven into the background hum of reality. The silent vibrations from those ancient collisions were not the only force sculpting the cosmos. While black holes danced and stars exploded, a far grander and more patient architecture was slowly emerging from the void. Gravity, the weakest of the fundamental forces, was engaged in its most ambitious project, weaving the entire observable universe into a single, intricate structure known as the cosmic web. This was not a swift creation, but a slow-motion catastrophe of amplification, where the tiniest of beginnings grew into the largest things we can see. Those subtle density variations imprinted in the cosmic microwave background, the quantum seeds from inflation, were the blueprints. Over billions of years, gravity relentlessly pulled on these slight overdensities. Regions with just a little more dark matter and normal matter began to attract even more material from their surroundings, growing heavier and pulling harder in a self-reinforcing cycle. The result is a universe structured like a vast sponge, a labyrinth of unimaginable scale. Gigantic, mostly empty voids spanning hundreds of millions of light years form the bubbles of this sponge. Wrapped around these empty spaces are the great walls and filaments, long, dense tendrils of dark matter and galaxies that stretch across the cosmos. And where these filaments intersect at the dense knots of this universal web, we find the most massive gravitationally bound structures in existence, galaxy clusters, each containing thousands of galaxies. This entire process was a cosmic tug-of-war. For eons, gravity's attractive pull dominated, driving the collapse and growth of this web. But as the universe expanded and thinned out, a mysterious repulsive force, dark energy, began to take over. This anti-gravity effect started to resist the collapse, putting a brake on the growth of the largest structures and accelerating the expansion of the empty voids. The cosmic web we see today is a frozen snapshot of this ongoing battle between the relentless pull of gravity and the pervasive push of dark energy. By mapping the filaments and measuring the voids, cosmologists can read this architecture like a history book. The specific pattern of the web tells us about the total amount of matter and dark energy, the strength of gravity, and the initial conditions of the universe itself. Every galaxy, including our Milky Way, is a single thread woven into this colossal tapestry, its position and motion dictated by the gravitational pull of the local filament it calls home. This grand structure, built over billions of years from infinitesimal ripples, is the foundational framework upon which all subsequent galactic evolution is staged, a silent, sprawling monument to gravity's patient power. For billions of years, gravity had been the universe's great architect, patiently pulling matter together to build galaxies and weave the cosmic web. But this era of construction was not destined to last. Around 5 billion years ago, a silent coup took place across the cosmos. A mysterious repulsive force, which we call dark energy, began to overpower gravity's relentless grip. This was not a battle fought with explosions or light, but a fundamental shift in the very fabric of space itself. The expansion of the universe, which scientists had long assumed was gradually slowing down due to the collective pull of all matter, did the unthinkable. It began to speed up. This discovery, made by observing distant supernova, completely overturned our understanding of cosmic destiny. We now live in a dark energy-dominated era, a phase where the fate of the cosmos is no longer governed by the pull of matter, but by the push of empty space. The consequences of this acceleration are both profound and lonely. As the expansion rate increases, galaxies beyond our local gravitationally bound group are being carried away from us faster and faster. Eventually, their light, stretched to longer and longer wavelengths, will no longer be able to reach us. They will fade from view one by one, receding beyond our cosmic event horizon. Billions of years from now, a future astronomer in our Milky Way galaxy will look out into a vastly emptier sky. The evidence for other galaxies and the great cosmic web that connects them will have vanished. Our galaxy and its nearest neighbors will be an isolated island in an ever-darkening, expanding void, with no clue that a universe of other islands ever existed. The true nature of this dark energy remains one of the greatest puzzles in all of science. Is it a constant energy inherent to the vacuum of space, or is it a dynamic field that could change over time? The answer will determine the ultimate fate of everything, from a final, frozen silence to a dramatic cosmic rip. This invisible force, whose dominance began around the time our solar system was forming, now holds the remote control to the entire universe, dictating a future of increasing isolation and darkness. Deep within the calm, stable heart of a star like our Sun, a quiet rebellion was brewing. For billions of years, it had fused hydrogen into helium, a steady process that provided the light and warmth for potential life. But all that time, the core was accumulating the inert ash of this reaction, a growing ball of helium that was not yet hot or dense enough to ignite. This helium core, shrouded by a shell of still burning hydrogen, became a ticking time bomb. As the core contracted under its own weight, it grew hotter and denser until it reached a critical threshold of 100 million degrees. At that precise moment, the dormant helium ash awoke with a vengeance. The entire core underwent a runaway thermonuclear explosion known as the Helium Flash. In a frantic burst lasting mere minutes, the helium fused into carbon and oxygen, releasing a staggering surge of energy. This was not an explosion that shattered the star, but a contained internal detonation. The sudden, violent release of energy in the core was so immense that it forced the core to expand rapidly, like a piston pushing back against the crushing weight of the star's outer layers. This single, brief event was a stellar crisis that fundamentally rerouted the star's destiny. It abruptly ended the star's expansive and unstable red giant phase, pulling it back from the brink. The star then settled into a new, more stable period of helium fusion, becoming a smaller, hotter star on what is known as the horizontal branch. This internal catastrophe is a perfect example of how a star's life is not a linear path, but a series of distinct evolutionary phases, each separated by a violent transition. The helium flash is a crucial pivot point, a reset button pressed deep within the stellar interior. It directly influences the star's final act, determining how much of its newly forged carbon and oxygen will be expelled back into space when it eventually dies. The carbon in our own bodies, a fundamental building block of life, was likely forged in such a stellar crisis and then scattered by the star's later death throes. This transformative flash, hidden from view within the heart of countless stars, proves that the most pivotal catastrophes are not always the most visibly dramatic. They can be quiet, internal revolutions that set the clock for future creations. While these stellar crises reshape individual stars, the galaxy itself was about to face a far more widespread and systematic threat. But a star's death is not always an internal affair. Some are executed from the outside. Drifting through the crowded core of a galaxy, a star can make a single, fatal mistake, wandering too close to the supermassive black hole that lurks in the center. In its final moments, the star does not explode from within, but is instead torn apart by an external force of unimaginable power. The black hole's gravity creates a tidal force, a difference in pull so severe that the side of the star nearest the black hole is yanked with vastly more force than the far side. The star is not simply swallowed whole, it is spaghettified, stretched into a long, thin stream of incandescent gas. This is a tidal disruption event, one of the most violent and spectacular executions the universe has to offer. The stellar debris does not vanish into the black hole immediately. Instead, it forms a frenzied, swirling accretion disk, a cosmic whirlpool of superheated plasma. As this material smashes into itself at near light speed, it heats up to millions of degrees, unleashing a brilliant flare of radiation across the electromagnetic spectrum. For months, this single event can outshine every single star in its host galaxy combined. a temporary beacon announcing the death of a star and the feast of a black hole. These cataclysms are more than just a cosmic light show. They are unique natural laboratories. By watching how the flare brightens and then fades, astronomers can weigh the invisible black hole itself, measuring its mass with precision. They can study the physics of accretion in real time, watching how matter behaves under the most extreme gravitational conditions possible. The light emitted from the swirling debris carries a forensic signature, revealing the composition of the devoured star and telling us about the types of stars that dare to orbit these dark monsters. A tidal disruption event is a fleeting, violent autopsy of a solar system, illuminating the dark heart of a galaxy for just long enough to read its secrets. This stellar destruction reveals the ultimate power of gravity, proving that even the most stable objects are fragile when they enter the domain of a supermassive black hole. 66 million years ago, a rock from space rewrote the entire history of life on Earth. This was not a slow geological shift, but a single, instantaneous blow from the cosmos. An asteroid or comet perhaps 6 miles wide, traveling at hypersonic speed, slammed into the shallow seas of what is now the Yucatan Peninsula. The energy released in that moment was beyond human comprehension, equivalent to detonating billions of the most powerful atomic bombs ever built simultaneously. The initial flash of heat instantly vaporized the ocean and rock at the impact site, while a colossal fireball spread across the continent, igniting global wildfires that consumed entire forests. The ground itself heaved, generating tsunamis that towered thousands of feet high, scouring coastlines thousands of miles away. But the most lethal effect was what the impact threw into the sky. A plume of vaporized rock and superheated dust was blasted high above the atmosphere, and as it rained back down across the entire planet, it heated the upper air to oven-like temperatures, turning the sky itself into a global broiler. Then, as the finer particles remained suspended, they blotted out the sun. The world was plunged into a prolonged impact winter, with sunlight unable to reach the surface for months or even years. Photosynthesis ground to a halt. The base of the global food web collapsed. This chain reaction of fire, darkness, and cold led to the Cretaceous-Paleogene mass extinction, an event that erased an estimated 75% of all plant and animal species. The most famous victims were the non-avian dinosaurs, the magnificent rulers of the planet for over 150 million years. Their sudden disappearance was a cosmic tragedy, but it was also an opening. The ecological niches they once dominated were suddenly vacant. In this shattered world, small, hardy, and adaptable mammals, which had scurried in the shadows for eons, found their opportunity. Without the constant pressure from dinosaur predators, they could diversify, grow, and eventually flourish, setting the stage for the rise of primates and, much later, humans. The Chicxulub crater in Mexico, a ghostly scar over 100 miles wide buried beneath the land and sea, is the silent witness to this pivotal collision. It stands as a humbling reminder that our existence is tied to events far beyond our atmosphere. The evolution of life on any world is not a guaranteed, safe progression, but a story punctuated by random, catastrophic interventions from the void. The same cosmic environment that builds stars and forges elements can also, without warning or malice, deliver a verdict of extinction. How different would our world be if that asteroid had arrived just a few minutes earlier or later, striking deep ocean instead of shallow, mineral-rich rock? This single impact demonstrates with brutal clarity that the fate of biology is intimately linked to the hazards of astronomy. Long before the dinosaurs, Earth endured a far more ancient and prolonged assault from the heavens. For hundreds of millions of years after the planets had first coalesced, a relative calm settled over the inner solar system. But that calm was brutally shattered around 4 billion years ago by a catastrophic event known as the Late Heavy Bombardment. It was as if the solar system itself had turned against its own children. A sudden, dramatic surge of asteroids and comets rained down upon the terrestrial worlds, a relentless hailstorm of cosmic projectiles. The evidence for this chaotic era is written in stone, preserved on the face of our own moon. Its heavily cratered highlands are a permanent museum of this violent age, a scarred landscape untouched by erosion or plate tectonics. Mercury, too, bears the same pockmarked testimony. For any world without a protective atmosphere or active geology, the Late Heavy Bombardment was the defining event that sculpted its final appearance. But what could have triggered such a delayed and furious onslaught? The planets were not always in their current, orderly orbits. Models suggest that Jupiter and Saturn, the solar system's giants, underwent a gravitational dance, migrating slowly inward and then outward. This planetary shuffle acted like a cosmic gravitational whip, violently destabilizing the vast reservoirs of primordial debris left over from the solar system's formation. It flung countless objects from the asteroid and Kuiper belts inward, turning them into missiles aimed directly at the inner planets. Earth, being the largest target, would have suffered the most. Its surface was effectively sterilized over and over again, melted into a global ocean of magma. Any nascent continents were shattered and remade. The very crust was pulverized, with the heat from impacts potentially creating vast subterranean hydrothermal systems. Yet from this absolute devastation, a paradoxical possibility emerges: the delivery of life's essential ingredients. These comets and asteroids were not just barren rocks, they were cosmic delivery trucks carrying volatile compounds. Icy comets, in particular, could have brought vast quantities of water to our parched young world, filling the basins that would become our oceans. More importantly, they also carried a rich cocktail of prebiotic organic molecules, the complex carbon-based building blocks necessary for life to eventually arise. This presents a profound and haunting question. Did the very same cataclysm that rendered the planet's surface a molten hell also seed it with the chemistry for a biological paradise? The Late Heavy Bombardment stands as a pivotal chapter in our origin story, a period of extreme destruction that may have paradoxically laid the essential groundwork for creation. The scars on the moon are not just a record of chaos, they are a silent monument to the violent birth of our world's potential. The fate of our world is sealed not by an external impact, but by the star that gives it life. Our Sun, the steady anchor of our solar system, has a finite supply of fuel. In about 5 billion years, the last of the hydrogen in its core will finally be exhausted, triggering a chain of events that will utterly annihilate the inner solar system. This is not a sudden explosion, but a slow, inexorable transformation. With the nuclear fires in its core extinguished, the Sun will no longer have the outward pressure to resist its own immense gravity. The core will begin to contract, heating up under the intense compression. This new heat will ignite a shell of hydrogen burning around the inert core, and the Sun will respond to this frantic new energy production in a dramatic way. It will begin to swell, ballooning outward to a size so colossal that its outer atmosphere will reach beyond the orbit of Earth. Mercury and Venus will be the first to be consumed, vaporized within the Sun's tenuous but searing hot outer layers. Earth will face the same fiery fate, its rocks and metals melting and dissolving into the stellar plasma. The very world we stand on will cease to exist as a solid body, its atoms return to the star that forged them long ago. As the Sun expands into a red giant, its luminosity will skyrocket, increasing 1,000-fold. The increased heat will blast the outer planets, boiling away the atmospheres of Mars and Jupiter and turning the icy moons of the gas giants into temporary, steamy water worlds before they too are stripped bare. The delicate gravitational balance of the entire solar system will be thrown into chaos, with planetary orbits becoming unstable and erratic. This violent expansion, however, is only a phase. The Sun will not have the mass to explode as a supernova. Instead, after a period of instability, it will gently shrug off its entire outer atmosphere. These expelled layers will expand into space, forming a beautiful and intricate cloud of incandescent gas known as a planetary nebula. This nebula will be a brief, glorious tombstone, glowing for only a few tens of thousands of years as it is illuminated by the intensely hot core left behind. That core, no longer supporting fusion, will become a white dwarf, an Earth-sized remnant of degenerate matter that will glow with residual heat for trillions of years before finally cooling to a black cinder. This stellar life cycle is the fate of over 97% of all stars in our galaxy. It is a universal catastrophe that systematically erases inner planetary systems, a final, definitive reset for any worlds that once orbited there. The death of a star is the ultimate conclusion for its planetary children, a poignant reminder that even the most stable and life-giving systems are temporary. This cosmic recycling program, while destructive, also enriches the galaxy with newly forged elements, scattering them into the void to one day become part of new stars, new planets, and perhaps new stories. The ultimate destination of our cosmos is not a fiery crunch or a dramatic rip, but a slow, cold sigh. Trillions upon trillions of years from now, the universe will approach a state of final equilibrium, a condition cosmologists call heat death. This is the ultimate triumph of the second law of thermodynamics, the simple but inexorable rule that states systems tend toward disorder. Every star, from the mightiest blue giant to the feeblest red dwarf, will have long since exhausted its nuclear fuel and faded to a cold, dark remnant. The last black holes, having feasted on galaxies for eons, will themselves evaporate away through a faint quantum process known as Hawking radiation, emitting their final particles into the void. With no more stars to form and no more black holes to anchor space, the universe becomes a profoundly different place. All the energy gradients that once powered the cosmos will have been smoothed away. Imagine a cup of hot coffee left in a room. It eventually cools to the ambient temperature, and no further work can be extracted from it. The entire universe will become that room, a place of uniform, frigid stillness. There will be no more hot sources or cold sinks, no differences in energy that can be harnessed to perform work. This means no more chemical reactions, no more motion, no more light, and crucially, no possibility for any form of life or complex process to exist. The cosmos will be a dark, ever-expanding sea of incredibly dilute particles and radiation, each photon stretched to wavelengths longer than the current observable universe. This is the quietest catastrophe imaginable, a final state where time itself becomes meaningless because nothing ever changes. While this fate is almost impossibly distant, it is the logical conclusion of our accelerating, expanding universe, a final, silent testament to the fact that all cosmic stories, no matter how grand, must eventually reach their final page. But even the silent end of heat death relies on a single, fragile assumption that the laws of physics themselves are permanent. What if they are not? The 19th cosmic catastrophe presents a doomsday scenario so absolute it challenges this very foundation, the theory of vacuum decay. Our universe might not be in its most stable, lowest energy state. Instead, it could be resting in a false vacuum, a precarious valley perched high on a cosmic hillside. This state is stable for now, but it is not truly stable forever. A random quantum fluctuation anywhere in the cosmos could act as a trigger, a tiny nudge that kicks the universe out of this false valley and into the true lowest valley below. This transition would not be a gentle roll. It would be a catastrophic and instantaneous phase change, like a supercooled liquid flash freezing in an instant. The point where this happens would become the epicenter of a bubble of true vacuum. This bubble would not be empty space, but space with a fundamentally different set of physical laws and constants. The very rules governing reality would be rewritten within its expanding wall. The bubble's boundary would expand in all directions at nearly the speed of light, and there would be no warning. One moment, the universe is as we know it; the next, an invisible sphere of new physics is racing toward us, utterly undetectable until it arrives. The moment this wall of true vacuum passed through our region of space, everything would cease to exist in any recognizable form. The new vacuum state would likely have different properties for the fundamental forces, the forces that hold atomic nuclei together, that allow electrons to orbit, that enable chemistry, might simply cease to function in a way that supports matter. Atoms could not form, or they would instantly disintegrate. The very concept of a star, a planet, or a living cell would become physically impossible. All structures would be erased, not into energy, but into a new, barren state of reality that does not permit complexity. This is not an explosion of fire and light, but a silent erasure of physics itself. The universe would continue to exist, but it would be a dead universe governed by new, sterile laws. While this is a highly speculative idea from the frontiers of theoretical physics, it serves as a profound and humbling reminder. The constants we rely on, the strength of gravity, the mass of an electron, the very charge of a proton, might not be fundamental truths etched eternally into the cosmos. They could be mere contingencies, the local bylaws of our particular cosmic neighborhood, our fragile bubble of false vacuum. Their stability is what allows us to exist, but it may not be a guarantee. It is a temporary grace period in a cosmos capable of far more radical change. Even the vacuum of space is not truly empty. It seethes with a faint quantum energy, a constant flickering of virtual particles popping in and out of existence. Normally, these particle pairs annihilate each other almost instantly, leaving no trace. But at the very boundary of a black hole, the event horizon, something strange can happen. If one particle of the pair falls across the point of no return while the other escapes, the black hole appears to radiate, slowly losing mass in a process known as Hawking radiation. This elegant solution, however, creates a monstrous puzzle, the black hole information paradox. In quantum mechanics, information is never truly lost. The precise quantum state of every particle that falls into a black hole should, in principle, be preserved, even if it is scrambled beyond recognition. But if a black hole evaporates completely through Hawking radiation, and that radiation is purely random and thermal, then that information would be irretrievably erased from the universe. This violates a fundamental tenet of quantum theory, forcing physicists to confront an uncomfortable choice. Either our understanding of quantum mechanics is wrong, or our picture of a black hole's event horizon is catastrophically incomplete. One radical proposal to resolve this is the firewall hypothesis. It suggests that the event horizon is not the smooth, uneventful gateway predicted by Einstein's general relativity. Instead, it might be a seething wall of unimaginably high-energy particles, a literal firewall that would instantly incinerate anything crossing it. For an astronaut falling toward a black hole, the difference is existential. According to classical physics, they would notice nothing special as they crossed the horizon, at least until tidal forces later pulled them apart. But according to the firewall idea, their journey would end in a flash of pure energy the moment they reached that invisible boundary. This represents a profound conceptual catastrophe, a direct conflict between our two most successful theories, general relativity and quantum mechanics. They cannot both be correct in this extreme environment. The smooth space-time continuum and the unwavering conservation of quantum information are at war. The firewall is a stark warning that our current laws of physics are incomplete. Resolving this paradox is not just an academic exercise, it is a necessary step toward a deeper truth, a theory of quantum gravity that would finally unite the very large with the very small. This final catastrophe is not one of exploding stars or colliding galaxies, but a crisis of understanding itself, forcing us to realize that the ultimate nature of reality may be far stranger than we have ever dared to imagine. Looking back across these 20 cosmic catastrophes, a profound pattern emerges from the chaos. The universe does not evolve in a gentle, linear progression. Instead, it leaps forward through violent phase transitions, each catastrophe acting as a necessary crucible for the next level of complexity. The quantum seeds of inflation had to be stretched to galactic proportions to give gravity a blueprint. The great annihilation of matter and antimatter had to leave a 1 in a billion surplus to provide the raw atoms for everything. The first stars had to die in spectacular supernova to forge the elements of planets and life. Even the asteroid that wiped out the dinosaurs was a brutal form of creative destruction, clearing the stage for mammals to rise. This is the hidden rhythm of cosmic history, a drumbeat of crises that build upon one another. Each disaster solves a problem created by the previous one, while simultaneously creating the conditions for the next upheaval. They are the universe's way of breaking old symmetries and unlocking new possibilities. This pattern holds true across every scale, from the subatomic flicker that becomes a galaxy to the death of a star that seeds new worlds. The same physics that governs the evaporation of a black hole also dictated the nuclear fusion in the first stars. This unity of physical law means that catastrophe is not an anomaly. It is the essential engine of cosmic evolution. It forges structure out of uniformity and diversity out of simplicity, guiding the universe on its long journey from a featureless fireball to the rich tapestry of galaxies, stars, and planets we see today. Yet this very same engine, having built such incredible complexity, now drives the cosmos toward its final, quiet state of equilibrium. The story of the universe appears to be a single, continuous arc, a narrative of transformative upheaval where creation and destruction are two sides of the same coin. Our journey through these 20 cosmic catastrophes reveals an undeniable truth, a universe forged in violence and meticulously shaped by upheaval. From the initial singularity of the Big Bang to the silent, cold whisper of heat death, these events are the architects of everything we know. They have dictated the fate of galaxies, sculpted the lives and deaths of stars, and determined which planets would flourish and which would be sterilized. They are the reason we exist, built from the elemental ashes of long-dead stars, and they are the reason our distant future appears so profoundly lonely. This narrative of destruction and creation places us in a humbling perspective. We are not the center of the cosmos, but rather a fleeting, beautiful consequence of its chaotic and impersonal laws. Our planet, our species, and our moment in time are a tiny, intricate pattern woven into a tapestry of unimaginable scale, a tapestry whose threads are spun from catastrophe. Yet, this understanding is not meant to diminish us. The study of these universe-altering events does more than just satisfy our innate curiosity about where we came from. It provides the crucial keys to understanding the fundamental laws that govern all of reality. Every supernova we observe, every gravitational wave we detect, and every ancient crater we map is a piece of a grand puzzle. By putting these pieces together, we are not merely learning about the distant past, we are uncovering the deep, underlying principles that dictate the behavior of everything, from the smallest quantum particle to the largest galaxy cluster. As our telescopes peer deeper into space and our theories probe the edges of physics, we continue to add new chapters to this epic story. We are uncovering more about these transformative events and, in doing so, learning more about our own improbable origins. The universe's entire history is written in the language of these cataclysms, and with every new discovery, we are just beginning to learn how to read it. We would love to hear which of these cosmic catastrophes fascinates you the most. Was it the Great Annihilation that left behind a universe of matter, or the asteroid impact that cleared the way for human evolution? Share your thoughts in the comments below.